Welcome to the 5 o'clock session. My name is Greg Kuhlmann, and so I lead a startup here in Austin called Sumatra, and we have a real-time machine learning platform that we use to help companies solve use cases like fraud prevention, recommendations, and we're currently focused on our conversion optimization product, which is aimed at growth teams. And so I spent most of my career in the real-time ML space. Previously, I was a data scientist at Apple, fighting fraud on the App Store and Apple Pay. And the way that anti-fraud solutions are built is really shaped the way that I think about real-time ML in general. And so this talk is just about sharing that perspective. It's hopefully useful to you, whether you're someone who's actually working in fraud prevention yourself, or someone who's maybe less familiar with how fraud prevention systems are built and working in some kind of adjacent real-time domain. So, all right, let me see if the slides work here. All right. So what we're going to talk about is what I would call like the 5 different dimensions of challenge that make anti-fraud machine learning pipelines particularly difficult, and have the 2 different high-level architectures that I've seen employed in the space to solve these kinds of problems, and then kind of bring it together and see what are the takeaways for real-time ML in general based on that. So the type of fraud that we're talking about here is really, transactional fraud. So meaning we're trying to make a decision, very quickly based on some transaction that's being attempted. So to give you kind of like a motivating example, so imagine you're running a marketplace where you have, unknown sellers that are joining and then putting up goods to sell, like say ebooks, for example. And then you have buyers show up, they bring their payment methods, and they buy these items. And so with each one of these transactions, the question is the risk of fraud that this, potentially a stolen credit card, is that high enough to actually block the transaction from going through to prevent a dispute? And how do you optimize that balance between false positives and missed fraud? So typically you would architect this by having your marketplace app call out to a service that's dedicated to fraud, and the marketplace app would be responsible for taking certain elements of the transaction, just kind of like the base level identity IDs that about the different entities, send them over to the fraud service, and the fraud service basically responds very quickly with whether you're going to allow that transaction or not. So if we kind of double click on that fraud service and look at what's going on inside, there's quite a bit typically that's happening in there. So it really starts with that raw input that we're getting in. And then typically what the next thing that you're going to do is extract the various entities that you care about. So in this case, things like the buyer, the seller, the particular payment method, the product ID, and so on. And then for those, you're going to have features that you're going to be computing that are going to be relevant to the risk. For example, with the buyer, you might care about how much money has totally been spent by this particular buyer, or for a particular card, how many different buyers have been associated with that payment method over some time period, for example, right? So those are kind of like the raw features that would then typically go into a model where you're going to apply often some kind of pre-processing, things like normalization, missing value replacement, and so on, which are typically part of the model artifact itself. That model will then output typically a fraud score or probability. And then very commonly, you're going to have some kind of post-scoring logic that's going to be business rules, things like allow list, block list, thresholds, stuff like that before you finally make your decision. And so something to recognize about this is it's actually just one big DAG, right? Or at least you can think of it as one big DAG. So you have all of these raw inputs come in, a bunch of transformations happen. Even the model inference itself is really just another transformation, all the way until you arrive at the final decision. So we'll come back to why it's important to think about that as a DAG later. So when I think about these kinds of problems, like what are the big operational requirements that in these cases are really not just nice to haves, but really necessities. And so I call them fast, fresh, scalable, consistent, and agile. And so we'll go into each one of those. So by fast, what I mean is that we're talking about low latency inference here, right? So from the time that you have a transaction attempt until you decide whether you're going to allow it or not, typically needs to be very, very fast, on the order of milliseconds. And the reason is for transactional fraud like this is you're in the critical path of making money, right? So you can't be waiting seconds typically unless you want to create a really bad customer experience. As far as applicability, for problems outside of fraud, really, like this still applies to a really like broad set of operational problems, really anything we might call real-time ML. But anything we might call like analytical machine learning, batch inference, things like that, obviously that's where this doesn't apply. And so if you're in one of those problems, then the problem actually gets a lot easier. You can do things like batch inference pipelines, pre-computing scores, things like that. So we're really not going to be focusing on any of those kinds of problems here. We're really focused on what we call real-time inference problems. So the other dimension is scalability. So what we mean by that is just high throughput, tens, hundreds, maybe even thousands of transactions per second going through the system. So why it matters, particularly for transactional fraud situations like this, is sometimes you're in the path of certain flows like login streams that are going to be very high throughput. But even in cases where you may have like average traffic fairly low, because you're in an abusive situation, you can just get hammered by fraudsters that are going to give you spiky traffic. So as far as like when this applies, it really kind of applies to a lot of our problems, right? And even if it doesn't apply to your problem, like most of what I'm going to say really doesn't depend on this this particular property. So as far as like the feature development itself, so what I'm calling agile here is when you're in situations where you need to make logic changes very frequently. So in the case of fraud prevention, probably the most frequent thing that happens is you have fraud analysts that are just updating rules where the models and the features just stay fixed. Maybe less frequently, but somewhat periodically, you'll still kind of keep the features the same, but maybe retrain the model on some new labels that you've gotten in recently. But in the case of like maximum agility, sometimes you're going to encounter some kind of fraud problem that just requires you to have a feature to look for a pattern that you just didn't even know to look for before, in which case you're probably updating the feature pipelines themselves as well as the models and then any rules that depend on those features. And so why this agility matters to fraud, it should be fairly obvious, which is that sometimes you're just under attack and you're just bleeding money and you need to be able to stop the bleeding really, really quickly. Also, you can never really rest on your laurels because you're in an adversarial situation. And so the fraudsters are always trying to adapt. They're always trying to look for weaknesses. And so basically changing your logic frequently is necessary. But this idea of having to update things regularly applies to not just adversarial domains, but really any non-stationary problem. And even in the case where you may have problems that are fairly stationary, if you're going to try to implement a lot of models and solve a lot of problems with a small team, your ability to get new features, new models into production quickly is going to be really important, right? So, if you don't care about this, right? If you really feel like, okay, I've decided these are the 10 features I'm ever going to care about, and I'm going to work on putting those into production, then a lot of the things that I'm going to push on here are things that you probably wouldn't care about as much, because the idea of having a separate implementation of training of the training data and the serving data might not be such a bad thing, because you're only going to have to implement those things once and then validate them once, and then you're good to go. So that brings us to this property of training serving consistency, or not having training serving skew, right? So what we mean by that is that the features that come in at model inference time are consistent with the model the feature values over historical data that are used to train the model. And so this is particularly important in fraud when because we're constantly changing and adding new features all the time. You often are going to be training a model on features that were not live for the full duration of the training period. So if you're going back, say, 6 months and you added a new feature 3 months ago, you want to be able to actually see what that feature looked like, for the entire training period. And the other thing is that label leakage is really a critical issue. So a lot of the features that you're going to see are going to be things that have to do with the association of some entity with some known fraud, like, or how many decline transactions did they have, how many rejections did they have, how many chargebacks did they receive. So if you were to do a use only the most recent values for those features instead of doing point-in-time joins on the past, you'd be leaking a ton of data about your labels back into the features, which would make it look like your model is performing much better than it actually would when you deployed it. So this idea of training serving consistency is something that's just sort of a general best practice, something you're always going to want to do, but it's particularly important for really high stakes use cases like fraud prevention when you're making some kind of critical decision. If you're doing something like maybe recommending a playlist or something like that, it'd say like the accuracy of the model may not be quite as critical. And so if this is something you don't need, again, kind of going back, you have this option of dual implementation, which is something that a lot of teams do, where you have the online versions of your features, and then you have kind of a separate implementation of those same features that's in maybe the online one's in Java and the offline one is in SQL, for example, something like that. Or the other option is you do log and wait, right? You have the online system, it's going to produce the feature values, and if they weren't there in the past, well, you just wait long enough and you're eventually going to log enough of those values that you're going to be able to have them backfilled and ready for training. All right, so finally on the last kind of most critical dimension that I want to talk about is this idea of freshness, which what we mean here is how low latency are the feature writes. And so if you have transactions coming in, like say login attempts by a particular IP address, what we mean by freshness is how soon after that failed login occurs are we able to be aware of that and make use of it in logic that's going to decide something about future decisions. And so why this matters for fraud is that often attackers will just hammer away, and so if that happens and the freshness is it's very stale, then you may not be aware of it for minutes or even hours, and which will cause you to miss quite a bit of stuff. And the other thing is just this concept of behavioral features of seeing multiple different kinds of events along a customer journey are highly indicative of what the intent of a user is, whether it's a super high value customer or whether it's somebody who is a bot, somebody just kind of casually browsing versus somebody who's really intent on buying, for example, right? So being able to leverage all that very recent data about how someone behaved, how they browsed, how they searched in your decisions is just going to make them much more accurate. So this is sort of like the most controversial of the dimensions in terms of how important really is freshness. And so the answer is that it definitely does not apply to all machine learning use cases for sure, right? It's highly use case dependent. It matters for things like fraud, security, trust and safety, but also things like session-based recommendations, personalization, conversion optimization, basically anything where really recent information about what the user is doing is relevant to your decision. And if you don't need it, then it makes things a lot easier in some sense, in that really all you need is batch feature pipelines, which typically with existing infrastructure are easier to support. So when it comes to the three critical ones that I call it here, freshness, agility, consistency, there tends to be a feeling that it's very difficult to achieve all three of them at once in a system. And so we as ML engineers often try to convince ourselves in every possible way, can we somehow give up one of these? In particular, freshness is usually the first one to go. But in other cases, maybe if we're going to do freshness and make sure that we have consistency, we kind of limit the ability of, say, data scientists to self-serve. So we're kind of limiting agility, for example. But it really is possible, and it's just barely possible to create systems that have all three of these. And this is kind of my first claim that I want to make, that this really is something that can be done. And so we should aim for it, because it's cool. So focusing on the freshness one, since that seems to be the sticking point in most cases. So I like to think of it in terms of similar to the data hierarchy of needs, there's like a freshness hierarchy of needs. So you look at ML teams and they start typically not even with batch features, but really actually with model embedded features. And so, for example, just at the time of training, you can just query your database, get something like some low cardinality feature, and you can just store it right in the model itself, right? So especially in these days of foundation models and LLMs, this is not really a foreign concept anymore because these models are so huge they can actually incorporate quite a bit of model embedded features. But for more classical ML, it still can be used sometimes. The limitation, right, is that, like I said, low cardinality, as well as you're only going to get as fresh information as how often you retrain the model. So people tend to, fairly quickly move on to using batch features. These allow you to have higher cardinality, but also they allow you to do things that are just more complex and more sophisticated, things that require like iterative algorithms, for example, like graph traversals or things like that. And so these are fine if you're going to do things that are refreshed maybe hourly or daily. And then when you need something that is refreshed faster than that, that's when you move to streaming. And so in the case of fraud, it might be something like the number of failed logins by this IP in the last 15 minutes, right? So it's a limited set of computations you can do. Typically, things like windowed aggregations, lookups, stuff like that. But these allow you to have features that are refreshed within seconds or even milliseconds. And then finally, kind of the freshest of the features would be on-demand things. So things that are only available in the input payload itself. And you're basically performing these stateless transformations on that input payload. So this perception of, or I should say, like the way that this maps onto the way teams tend to develop these features is, right, we're thinking about these in terms of staleness versus freshness, but it also tends to be the case that the things lower on the freshness scale tend to have more use cases. They're more broadly applicable. As we said, real-time data tends to be really important for a restricted set of use cases. And at the same time, batch features tend to be easier to implement, whereas streaming features tend to be harder to implement. And so when you combine those two things together, something that is less applicable, it's seen as harder to implement, then when it comes to a team kind of building up a platform internally over time, the first things they're going to implement are going to be more on the batch end and sort of move towards streaming and faster features as necessary. And so those will be the last thing to implement. So when you look at kind of the evolution of a platform within a team that's kind of evolving in this way, typically it starts with a model service, right? Maybe they just stand up a service in Python, Kubernetes. And then when you need batch features, you add in some ad hoc pipelines that, after a while, maybe turns into a bit of a, spaghetti code mess. And so you kind of tame it with a feature store to kind of share features between models. Then what you find is maybe as you're hitting issues with freshness, you kind of push the batch features as quickly as you can possibly go, but without really making any fundamental change to the architecture. So I just call this, cron go faster. But eventually you're going to hit some limit with that. And so finally, when you cry uncle and say, fine, I'll add streaming, knowing that you're kind of introducing a lot of complexity at that point. And so what the kind of next claim that I want to make here is that this hill climbing that teams often go through often leads to outcomes at the top of this at the end of this journey where they're sacrificing quite a bit in terms of agility and consistency in order to achieve that freshness and kind of arriving at this local maximum. And so the claim that I want to make is that if we can look at the way that fraud systems tend to evolve, we might be able to find architectures that are more amenable to these real-time problems and help us arrive at sort of a more global maximum. So if we look at the way that anti-fraud solutions evolve within teams, they're basically exactly opposite of how we saw that evolution of typical ML platforms. So it starts really at the highest end of doing the simplest on-demand feature first, right? So their first fraud API may be, hey, I'm just going to review every order that's over $100, right? So they'll stand up a service that just does a simple, stateless transaction, or a stateless transformation, which is, a rule, right? But they've already wired this thing up now, right? So they have this end-to-end thing that they can just iterate on and improve, right? So typically the next thing is, well, those stateless transformations aren't good enough. So I need to add some kind of stateful transformation to be able to do better than that, to achieve more accuracy, right? So to add counters, velocities, things like I want to know the sum of the amount by this particular payment over the last 14 days, for example. And so what I'm showing you here in these examples are it's code from the DSL that we've developed for our platform, and so it's just to make things concrete throughout the talk. So then, oops, sorry. So then typically where that hits a wall is when you want to be able to extend beyond the aggregation windows that are supported by things like counters, and then you say, okay, fine. At that point, I'm going to introduce the complexity of batch feature pipelines, do things like lookups to do things like graph traversals and load that data in, and then look that up as a batch feature. And then finally, well, sometimes between 2 and 3, or sometimes at the end, you move beyond sort of rule-based systems to actually developing a model. And so it's at this point typically where teams have they have freshness. They're using very fast counters and velocities. They have agility, so even non-engineers are able to put new logic into place really quickly. Where they fall down is when it comes to the consistency, right? Building a consistent training set for developing models. That is where the real problem comes in with these kinds of architectures. And so, so the question is, how do we, building from this top down, how do we build a consistent training set using this kind of approach? And so the answer that I'll say is basically what we call replay. So to explain what I mean by replay, we have to go back to our friend here, the DAG, right? And so what I'm showing here is, again, some more code in our domain-specific language, where you're doing this set of transformations of, you're taking this input feature of a seller email, you're converting it to an email domain, you're then computing a couple of different stateful aggregates over that, and then you're doing another stateless transformation to divide those through each other. So again, this is a DAG that is being deployed in real time to be able to compute the features necessary to go into our model. And so what I'm calling a real-time first abstraction is one where we have one of these DAGs for each of the different event types that we will potentially see, and that they're all kind of collectively compiled together and aware of each other. And so when we describe the logic of, say, what's going to happen at purchase time, we may have some features that we're going to compute, like I want to know the latest time I changed the billing, or I want to know the number of logins that failed for this user over the past 2 days. So if we describe those features at purchase time, what's actually happening behind the scenes is we can say, well, I know that I'm going to need to know this about billing information changes. So on the update billing event, I need to add a feature right. Similarly, what the compiler will do is look and see, oh, at login time, I know that I'm going to have to keep track of the number of failed logins, so let's add another feature right for that by email. So then, when it comes to online inference, right, we have all of these different DAGs ready to go as these processes that are running. And when a update billing event comes in with a certain email, then we know, okay, we need to write that down and say, for that feature, for this key, we're going to stick that in our online store. And then a login comes in, let's say, we're going to then update the online store again. So then when a purchase comes in, we're already ready to fetch that feature back out by the given key, and then use that at purchase time to have very fresh features with very low latency. And so here to make this possible, the aggregation is happening largely at write time, with some amount of kind of last mile aggregation happening in the read as well. So that's what I'm calling the real-time first architecture, and this is what it looks like in an online setting. So the question is, okay, so how do we achieve consistency with that? So what we need to be able to do is do the same thing, but do it offline. And so in this case, what we mean by offline is that we are assuming that we have a log of all of the past events that have come through that we potentially want to use in our training data. So you can think of these as like different tracks of a song. So we have like every update billing event, and purchase event, and login event that happens over time. So conceptually, what we do is we take that entire log from as far back as we want to go, and we just shove that thing into all of our DAGs as fast as we can to recompute all of the features from scratch till we arrive at our training data. So that's not scalable, it's not practical, but conceptually, that's exactly what we want to do. So practically what we can do is we can take these various DAGs, and the query planner can decompose them based on the dependencies. That's sort of the first optimization. The second one is that after we've computed a feature, if nothing else has changed, if none of its dependencies have changed, we'll never have to recompute that again. And so we can just fetch all the unchanged features from the cache. And then when something does change, we introduce a new feature, we change one, and then we want to do another replay. We can compute what is the smallest possible diff, what are all the smallest set of features that we need to recompute to be able to arrive at a consistent answer again. And so that's exactly what we do. So then the question may be, okay, so what about the case of batch features? How do those fit into this, right? So if, for example, you wanted to add a new batch feature that wasn't present at the time of inference, and so you have some ideas for some new data that you want to include, and so you have a historical record of those feature values in an offline store, and then in this framework, the way you think about it is each update to those tables is effectively just another event. So you can think of it as adding another track to your song, right? And so when you mix in that new track to your song, you treat it just like any other event during the replay. And so now that you have a lookup feature at the time that you want to read from it, combined with those new events, you get the features computed with effectively a point-in-time join, just as you would expect them to be. All right, so for the sake of time, I won't dig into too much about the engineering details about how we've actually implemented this on top of AWS serverless components. But based on the slide, you can pause it and dig around if you want. Also, if you're interested in learning more about the domain-specific language we developed for the features that have been showing in this talk, we have public docs on that. So it's at docs.sumatra.ai/scowl. And so to wrap things up, for these 5 different dimensions that are really necessities in the case of doing transactional fraud, this real-time first abstraction that has been motivated by anti-fraud systems really achieves all of those simultaneously, really out of necessity. And so, I talked a lot about all of the upsides of this, and I don't have rose-colored glasses here. There's definitely some challenges that come along with this that I haven't really focused on. Things like the fact that it's taken a lot of effort to develop this domain-specific language, to build out a standard library for this, knowing that to be able to achieve the speed and replayability, we need to be able to have all of this be able to live inside basically a very predictable set of components without just bringing in libraries from all over the place. And then taking this architecture that we, like I said, motivated by fraud prevention systems, we found it to be highly applicable to a wide variety of problems in real-time ML. So we're using it today heavily in web personalization, but also things like session-based recommendations, dynamic pricing, and so on. So if you have any questions, very happy to answer them. I'm happy to connect on LinkedIn. Here's my email. Always excited to talk about this stuff. Anything that people want to chat about when it comes to real-time ML, I'm definitely up for it. So thanks a lot.